Hello, welcome to the 5th lecture in category theory. In this lecture, we're going to look at yet another concept, but we will link it up with the previous lecture with the concept of adjunction. I did say last time that there is more about the junctions we need to understand, and that we will do a little bit today, but also a bit more in the future when we're going to come back to the concept of adjunction and look at it from other perspectives as well. The concept for today's lecture is that of a limit. Now, as we have agreed, the notion of a category emerges as a simultaneous generalization of the notion of a monoid and the notion of a preorder. And so there are some concepts that are inherited in a category that come from the notion of a monoid, and others that are inherited in a category coming from the notion of a preorder. So this one, the notion of a limit, comes from the preorder side, and in some sense you can think of the monoid side as being kind of the algebraic origins of a category, and the preorder side being the geometric origins. And limit, of course, is a geometric notion. And so we will begin explaining what a limit is in the context, first in the context of a preorder, where it simply becomes the notion of infimum. So let me draw a picture. If I have a few objects in a preorder, I might be interested to consider an object that is less than each of these. So remember, this arrow represents that one object is less than another in a preorder. But then I might want to consider the largest object that's less than all of those. So if my starting point is a set of objects in the yellow area, I'm considering all possible objects that are less than everything in the yellow area, but then taking the largest such. So if I have another object that's less than everything in the yellow area, then I'm requiring that other object will always be less or equal to the one I selected. Let's illustrate this idea on the example of the preorder of real numbers. So preorder of real numbers looks like a straight line. In that preorder, any two objects are comparable. Either one is less than the other or the other way around. And now on the real line, let's take all objects that fall in the interval. Well, actually, let's make it an open interval. In the open interval, let's say 1, 2. So my yellow area now is the set of all the numbers x that is bigger, strictly bigger than 1, and strictly less than 2. Which will be the object or real number that will be less than everything in the yellow area, but that will be biggest among those that is less than everything in the yellow area? Well, of course, all of these I'm drawing now, they are all less than everything in the yellow area. The red ones here, they're not. Neither are the red ones inside the yellow area. They're not less than everything in the yellow area. There might be less than something in the yellow area, but not less than everything in the yellow area. What about the borderline here, the number 1? Well, according to the definition of this yellow set, number 1 is indeed less than everything in there. But at the same time, so remember these arrows, the white arrows here on the left side of the board, they represent the relation of being less or equal to. So 1 is less or equal to everything in the yellow area. Moreover, it's actually strictly less than everything in the yellow area, but that's not relevant. But at the same time, it's bigger or equal to anything else that's also less or equal to everything in the yellow area. Because, in fact, the things that are less or equal to everything in the yellow area are exactly the points in this purple shaded region. And you can see that the points in this purple shaded region include number 1, and the number 1 is the biggest among all of them. Of course, in calculus or in analysis, we call number 1 then the infimum of the set. So we will say that 1 is infimum of the set. And the fact that 1 is the infimum of the set can also be expressed by the idea that 1 will be actually a limit of a sequence of selected points in the set. Those points that try to break the boundary of this yellow set on the bottom boundary, but never actually do. So they remain in the yellow set, but they try to come as close to the boundary as possible. That sequence of numbers will have limit 1, and that's the motivation for the term limit. So let's now state the definition in a general preorder. I already have a picture that defines what a limit is in a preorder, but let's write it out more formally. So given a set S of objects in a preorder, its limit is an object L such that 2 properties hold. The first one says that L is less or equal to S for every S in the set S. And the second one says that if some L prime is less or equal to S for every S in S, then that L prime must be less or equal to L. So the first one says that L is smaller than everything in the area, and the second one says that it's the largest one that's smaller than everything in the area. I do want to give another example of the notion of a limit in a preorder, which is going to be different from the one we gave here, in that in this example, it's no longer true that every 2 elements are comparable. So let's take again the realm of numbers, but we're no longer going to think of it as being linearly ordered, because the relation we're going to consider is the divisibility relation. So let's take 2 numbers, let's say 6 and 9. Or maybe to make it a bit more interesting, let's take 15 and 25. And the relation is the relation of basically the relation divides. So x is less or equal to y when x divides y. In other words, when y is equal to x times z for some z. And here we are working inside the set of natural numbers. So what are the natural numbers that are in this relation with 15 and 25? So the set I'm considering now consists of these two objects, 15 and 25. Let's draw all possible numbers that are less or equal to 15 and 25 simultaneously by this relation I've defined here. This will be, in fact, there will be only two of them, right? There will be 5 and there will be 1. If I make it a bit more complex, maybe I multiply this by 3 on the other side and multiply this one deliberately by a different number 2. Then we will also get that 3 is such a number, right? So 3 is less 3 divides both of these numbers. 15 is already divisible by 3, and here we multiplied by 3 in order for that 3 divides that. 5 divides both of these numbers. Which other numbers are such that divide both of these? Are there any more? So the way to figure this out is to decompose your number into prime factors. So 15 times 2 equals 3 times 5 times 2. And 25 times 3 equals 5 times 5 times 3. And then we see that we have 3, we have 5, and we also have 15 because we have both 3 and 5, right? But that's all. We don't have any other common divisors. Now, which number is largest among all of these? Well, of course, it's the largest common divisor, right? So this is usually called greatest common divisor. So the limit, in other words, will be the LCD of all the numbers in your set. So the picture looks like this. It's going to be a bit complex. So we have all these things that have arrows in both of them. And these are the only ones that have arrows in both of them. And among these, everything is related with 15 with an arrow. Well, 1 is even related with 3 and 5, but 3 and 5 among themselves are not related. Okay, so we now have two examples of limit of objects in a preorder, but what happens if I move from a preorder to a category? Let's first try to see how we should involve the algebraic information in the definition of a limit. And let's consider an example of two objects. So the question is, how do we sensibly generalize this to categories? So if I have two objects, x and y, their limit should be something that I'm going to denote by lim and the set xy. And remember, the requirement is that it must be less than both of them, so we must have arrows. And then it must be biggest among everything that's less than both of them. So if I have something else that's less than both of them, then this something else must be less than that as well. But in a general category, the arrows are no longer the less or equal relation. It's we can have multiple arrows between every two objects, and we have also composition of arrows. So we want to turn this notion of a limit to make it a bit more algebraic by introducing composition as part of the definition of the limit. And then the condition says that the limit, well, firstly, because you don't just have one arrow, you might have several. To define a limit, you need to choose some specific arrows, and let's call this the chosen ones P1 and P2. We might have others as well here, but we choose specific ones, which we didn't have to do in a pre-order, because in a pre-order, if we had an arrow, such arrow was unique. So if I said I have to choose something, then the choice would have been obvious, because there would be no choice. Basically, I would have to choose the one that's already there, and the unique one that's there. So the limit should be of this yellow area. It should be an object together with chosen arrows into every object in the yellow area, with the condition that if I have another object C with two chosen arrows, let's say F1 and F2, then there must exist this arrow here. And now I'm going to require that this arrow here is unique. And it's unique with a certain property. So that there exists unique F such that, and this is where I involve composition, such that P2 composed with F equals F2, and P1 composed with F equals F1. Okay, so what is the definition? So in the special case, the limit of this set of objects xy there is another thing that I'm not discussing yet, namely that in the case of pre-order, when I have two objects that are the same, let's say I've got x and y that are the same object, then of course my picture then becomes just this, and then of course the largest thing that's less or equal to everything in here will be just that point. But it turns out that with this more refined notion in a general category, that is no longer the case, that the limit of x and x will be just the same x. And so although the limit of only one x will be x, but not the limit of two x's. So what I'm trying to say is that we're no longer looking at a set of objects, we're looking at a family of objects, or you can think of it as a sequence of objects. So I'm going to then replace my notation here from set notation to a sequence notation. So a limit of the pair, the ordered pair xy, is a triple consisting of some object L. So this is my L, and arrows P1 going from L to X, and P2 going from L to Y. And maybe if I'm thinking of this as a sequence, maybe it would have been more natural to denote these objects by X1 and X2. Such that for any other such triple of object C and arrow F1 from C to X1 and arrow F2 from C to X2, there exists a unique arrow going from C to L for which those composites are equal. there is unique arrow F going from C to L such that, so I'm not saying that there is only one arrow from C to L. I'm just saying that there is only one with the property I'm going to write right now. There is unique F such that P1 composed with F equals F1 and P2 composed with F equals F2. Okay, so I've motivated the notion from the case of preorders where it seemed to be something natural. Then I stated the general definition in a general category by using some ad hoc, and not properly motivated adjustments to the definition, which in the case of preorder still becomes the same notion of a limit, but in a category there could have been many other ways of incorporating the algebraic data into the definition. Why did we choose this specific one? And in fact, the answer is that this notion historically did not arise from generalizing the notion of a limit from a preorder. It arose more from understanding the notion of a product of mathematical structures. And we will now see that in the category of sets, the definition that we gave here will give exactly the notion of Cartesian product of two sets. So this notion in the category of sets will become the notion of Cartesian product of sets, and we can confirm this by a proof. So I'm claiming that if I put in the place of L, I put Cartesian product of two sets. In the place of P1 and P2, I put what usually is called pi1, where pi1 is a function that maps an ordered pair x1, x2 to the first component, to x1. And then there's also pi2 function that maps the same ordered pair to x2. And the condition we need to check is that if I have another set with two functions, f1 and f2, that there will be unique function f having the property. So once again, I'm not saying here that there is only one function from C to the product. I'm just saying there is one with the requirement that pi1 composed with f equals f1 and pi2 composed with f equals f2. And once I spell out these requirements, I will indeed see that such function is unique, and it does exist. So let's write what this means by applying both sides of each equality to elements. So what are we saying here? We're saying that pi1 composed with f of an element C must equal f1 of C, right? And here we're saying that this must equal f2 of C. But that pretty much defines the function f uniquely, doesn't it? Because the function f would map an element C. So following the geometry of the previous picture, function f would map an element C to some ordered pair. Let's call this ordered pair x1, x2. And then when I apply, so this is my f of C, right? And then when I apply pi1 to it, it basically tells me what the first component of that ordered pair is, right? And it tells me that it must be f1 of C. So it tells me that this must be f1 of C. On the other hand, the other equality says that that thing must be f2 of C. So this one is x1 and that's x2, right? And this second equality says this must be f2 of C. So on the diagram, this being mapped to x1 by pi1 and that being mapped to x2 by pi2, and then requiring that this composite mapping should give me the same result as the mapping by f1, which does give me f1 of C, right? So that basically says that we're now claiming that there is a unique function f from C to the product x1 times x2 such that fc equals the ordered pair f1 of c comma f2 of c. And of course this is true, there is unique such function. Well, how do I know such function exists? Well, this is the definition of the function. How do I know it's unique? Well, because I have a very explicit definition for it. So there can't be another one. I'm saying literally what all the values must be, right? Remember, the f1 and f2 have been given to us in advance, and then using those, we were supposed to produce an f that's unique with the property that these composites are equal. And so if we already know what f1 and f2 are, then of course this equality, which is just a reformulation of commutativity of those triangles, so this triangle and that one, this equality does define, and moreover, it defines unique f. There is also a nice number theoretic way of understanding this idea. Imagine you start counting how many elements you've got in your sets. So let's say we've got in x1 we've got 3 elements, and in x2 we have 5 elements, right? In the product we'll have 15 elements. Now let's take another random number c. Let's say we take c to be 7, right? Now when I say that for every f1 and f2 there is a unique f having a certain property, namely having this property, keep in mind that also backwards is true. If I start with some g, right, I can always compose the g with pi1 and pi2 to generate some g1 and g2. So any function from C to the product arises as the solution of the problem of some pair g1 and g2. So what I'm trying to say is that if I now start mapping pairs of functions, so consider the set of all pairs of functions f1, f2, and then the set of functions from C to there. So let's use this usual set theoretic exponential notation for the set of functions. So if x1 to the power c denotes the set of all functions from C to x1, right? Then the Cartesian product of that with x2 to the power c will be the set of all such pairs, f1 and f2. And now I'm saying that for any pair f1, f2, there is a function from C to that Cartesian product, right? So I'm basically establishing a function. Sorry, this is just a function from here to x1 cross x2 to the power c. So what does this function do? For every f1 and f2, it creates the unique f. And this function must be injective because f is unique for each. Sorry, what am I saying here? It's not injective, it's just a function. But what is injective is the process backwards. So I also have a backwards function here that takes a g and maps it to the composites pi1 g and pi2 g, right? And so this backward function is going to be injective. Why is it going to be injective? Because if I had two different g's, let's say g and g prime, such that their composites with pi1, pi2 are the same, so on one side g1 and the other side g2, then remember, by the definition of the limit, there must be unique middle thing here, and so G1 must be equal to G prime. Sorry, G must be equal to G prime. So this function going backwards is injective. This function is injective. But then it's also surjective because we're saying that for every F1 and F2, such a G exists, right? So we basically have a bijection going backwards. And so maybe that's what I wanted to write here, not this direction, but the other direction. So we have a bijection between these two sets. If we start counting the elements in these sets, with taking this special example where x1 is a set with 3 elements and x2 is a set with 5 elements and c is a set with 7 elements, then of course when two sets are bijective they will have the same number of elements. Now let's count the number of elements here and there. So how many elements do we have here? The number of functions from C to x1 is equal to the number of elements of x1 to the power the number of elements in C. So that will be 3 to the power 7. And of course, when you take Cartesian product of sets, the number of elements multiply. And so here we have 5 to the power 7. And because the two sets are bijective, we get that these numbers must be equal. And what we recognize here is, of course, an important rule for exponents, how exponentiation interacts with multiplication. So this is another way we can think of this notion, and it kind of motivates why did we require this existence of a unique f here. Otherwise, if we didn't, then we wouldn't get a bijection here. So we can really think of basically we can think of this notion of a limit in a category of two objects as a way to generalize the idea of multiplication of two numbers to a general category in such a way that the definition for multiplication is basically this specific rule for exponents. It's almost like used as a definition of multiplication. Okay, so you see that this concept has lots of different roots and different ways of motivating it, and it's a very important concept in category theory, and we now want to move to even more general scenario where we not just have a sequence of two objects, but an arbitrary diagram of objects and arrows. But before moving there, let's make sure this part is understood well. So I would like to ask you if you have any questions on what we've been talking about, just to make sure that I didn't skip over anything that might not have been very clear to you.
I'm just not very clear about the choice of naming these limits. Does it have some connection that I'm not seeing with limits in, say, topology or analysis?
Yeah, that was kind of clarified here in this example. So
here we have unordered sets, but I'm used to having a limit of some sequence.
Yes, so if you take one of the basic examples of a topological space, which is the real line, right? If we consider the set of numbers 1 over n, where n is an integer, you can think of this as a sequence, yes, and its limit is 0, right? But then this order theoretically, so the infimum of this set is also 0, right? So the infimum coincides with the limit of 1 over n as n goes to infinity.
Yeah, so I can see how it coincides in a very, very special case.
Yeah, and that special case is used as a motivation. So if you have a general, are you asking the question for a general topological space?
Well, yeah. So from this example, it just seems to me like we should have called it an infimum, not a limit. It's just that there's this one case where the infimum of some set is the same
But
as the limit of making that
why
set a
don't we?
sequence.
But why don't we? I mean, the notion of a limit in topology is also generalization of this special case from the real line, right?
I guess my problem is just that usually we have limits of some sequence. We have some very specific
Yeah,
ordering of our elements that we
yeah,
do not have here.
Yes, and as you saw, we when we moved to a general category, we were forced to introduce the ordering, right? So the ordering comes in. The ordering is not visible in the case of a preorder, but it comes back in the case of a general category.
Okay, and so this ordering, if we just kind of blindly generalize this to some infinite set of objects in our category, and we have this infinite tuple, then this will, in some sense, correspond to the limit of that sequence. In the more intuitive sense of a limit versus the categorical sense that is used by describing this universal property.
Sorry, I think I didn't understand the question.
So we spoke here about two objects. We take the limit of two objects, and so we have some ordered pair, and that this can quite easily be generalized to arbitrary objects. I think that's quite clear.
Arbitrary
and
number,
so it's not clear to me that this can be extended to infinite objects, but I don't also see a reason why it can't be. And so if we have some infinite ordering of objects, then it starts gelling more with my usual intuition of what a limit of some, you have a limit of a sequence, right? So that just that very basic kind of first year definition of a limit. And so my question is there then some, in which category does this coincide with what we would usually call a limit? Is there some, can we make a category out of a topological space that this somehow makes the limit of some sequence the same as the limit of the tuple, the infinite tuple of the objects that represents the points? Or am I overcomplicating it?
So the link is not so straightforward, maybe. I also feel that you're asking an interesting question, and I feel that I don't have as interesting answers the question, but it might just be that there is a hole in my mind this morning. But when we will introduce arrows in our yellow area in the diagram of objects, then we will have another comeback to this idea of a limit, which will be through the category of sets this time, not the preorder. Maybe there your answer will, your question will be answered. So can you just hold on a bit more? So we'll come back to that question, Jean. Thanks. That's an interesting question. Anyone else would like to ask anything? Okay, so in fact, yes?
Oh, yes. With this exponentiation law, that one, 7 times 5.
So can you please try to be a bit louder?
Okay, can you hear me? Can you hear me now?
Now it's better, yeah.
Okay, you see that exponentiation law is just a fancy way of establishing the equivalence, yeah? I mean, the bijection between that product, yeah, between x1c, or the maps from C into x1, all those maps C into x2, yes. And so this this exponentiation law, this you know, similar to so how would you, I mean, so how does it boil down to the familiar, you know, that familiar one that is seen in undergrad maths?
What is the familiar one we see?
So that one that you wrote, you know, 3 to the 7 times 5
Yes.
to the 7 times, yes, times 3 times 5 to the 7. So you see, in the undergrad maths, there was so much effort that was taken into constructing that exponential function. You know, the exponential function, but this construction does it so elegantly.
So here, firstly, here we're only dealing with exponents when the numbers are natural numbers. So we're not going into the question of how to take exponents of fractions and irrational numbers more generally. And the other thing is that here we're thinking of exponentiation as just counting the number of functions from or the number of morphisms from one object to another object. So it becomes more kind of reducing, and moreover, kind of using exponentiation as the more fundamental operation than multiplication, and defining multiplication in terms of exponentiation in some sense. We've defined here product of two objects in terms of arrows, right? And arrows live in these exponents of sets. So it's kind of turning things around completely in a way. So yeah, I don't know if I've answered your question, but we're looking at it, I think, from a completely different angle than the angle that one usually uses to approach exponentiation of numbers.
Okay, thanks.
Okay, so what would happen if I took a more complicated situation, maybe suggested by Jean's question, having infinitely many objects here as well, but not just objects. What if there are also arrows involved there? So let's draw something complicated. In fact, maybe let's actually do I'm thinking whether we should do one more example, or no, let's actually move to the general definition first, and then we can specialize to further examples. So imagine this yellow diagram we start with is something quite complicated. So there could be several different objects there. But we said that it must be a sequence rather than a set. So there is some picture that is going to index. So my indexing set will no longer be just a set of natural numbers. Here, my indexing set was just a set of 1 and 2. But here, in a more general situation, my index will be an entire picture of objects and arrows. And let's just consider a picture like this. But you could have much more complex story here. You could have many arrows going in one direction or going in reverse directions to each other. In fact, let's take this infinite chain. Let's imagine this goes on infinitely. And then we take this picture. So a picture like this is called a graph in category theory. So you can really think of it as a directed graph, where you allow multiple edges between vertices, and also, edges going in reverse directions. And now let's interpret this picture inside a category by giving some names to to the objects and to the arrows. So and sometimes I might give same names. So if I introduce labeling of these vertices before they become objects in my category, like that, then once they turn into objects, they become C1, C2, C3, C4, C5, C6, and so on, C7, and it goes on like that. And then I also want to have some names for the arrows that connect them. So let's call this thing F1, F3, F5. So sorry, what am I doing here? No, I want to call them maybe like this: F1, F2, F3, F4, F5, and so on, F6, F7, and so on. So this part here is not residing in a category yet. It's just a picture of objects and arrows. And then I can interpret in a category where these arrows become actual morphisms. And then I will call these, let's say, G1, G2, G3. In fact, if I want to be maybe more consistent in my notation, I'm going to use the following labeling. So I'm going to call this D1, D2, D3, and these ones I'm going to call D of F1. So basically, I'm kind of thinking of my D operator as a functor, except that now this functor has its domain to be a graph, so something that doesn't have the structured composition. So it just maps arrows to arrows, objects to objects, which preserves domain and codomain. So such a thing is called a diagram in category theory. So D is the diagram here. So it goes on like this. And now I want to define the limit of this diagram. So limit will be, so I can, in fact, I can denote this by lim D. It will be an object together with specified arrows. So maybe just to be consistent with our infimum intuition there, I'm going to draw this limit below the diagram. Maybe I'm going to put this one above. There we go. So the limit of the diagram D will be an object with specified arrows, one for each vertex of my directed graph. So these arrows will be indexed by the objects of the directed graph, just like in a natural transformation. Pi1, Pi2, Pi3, Pi4, Pi5. And moreover, I want now also to take into account composition. So I want every single triangle that's formed here, I want that triangle to commute. So I will require that for any arrow f from n to m in my graph in here, d of f composed with pi of the domain of pi n equals pi of the codomain. So this is supposed to be true for all f's, and this will ensure that all of these triangles that you see in this picture, all of these triangles are commutative triangles. So that's my setup for a limit. And something like that will be a limit if another data of that kind, so if an object C together with specified arrows that satisfy a requirement similar to this, so let's call these specified arrows, let's say G1, G2, G3, and now you see the picture gets complicated. So maybe I will use a different color for that. So if I have this situation with more arrows going to the further objects that have not been drawn because I didn't think of any of them. So every such, for every G, and I'm calling this whole thing, this blue thing G, because it's just one thing, namely a family of arrows, of the blue arrows, that's indexed by the vertices of this original graph. So for every G, but it must be, a G must be such that a requirement similar to this holds. In other words, df composed with gn equals gm, once f is an arrow from n to m. Okay. So for every such G, there exists unique, so I'm now requiring that there is a unique arrow here, which I'm going to just call maybe G bar. There exists unique G bar going from C to this limb D, such that okay, so let's go back to the previous picture. So when I said that there is unique arrow here, I wanted these triangles to commute. So when I transition from C to the product, and then compose that with the corresponding linkage from the limit to one of the objects in my yellow area. Yeah, recall this is my yellow area. That composite must equal to the linkage of this object C to the object in the yellow area. So I want that, what I just said means that I want these triangles to commute. So I want this composed with that to equal that arrow. So this triangle will commute. Also, this triangle will commute. This triangle will commute, and so on. So there exists unique G bar such that pi n composed with G bar will equal to Gn for every vertex n in the graph. So this is the way the notion eventually becomes in its most general form in a category. But as you see, the definition is quite complex. In order to state it more beautifully, it would be useful to have some specific terminology for each of the ingredients. Like, for example, this collection of blue arrows is usually called a cone over the yellow area. The yellow area itself, which was designed from a directed graph, is called a diagram. So we'll have to define what a diagram is, and so on. But before we set up all these definitions, to be able to state the definition of a limit more elegantly, and in fact, let me also say that it's also possible to reduce these definitions to the notions of functors and natural transformations. But before going into that, let us look at some other examples to understand the intuition behind this process. So I'm now going to so here we had an example where we had two objects, right? And kind of almost like opposite to that, now we'll have an example with just two arrows. So imagine my blue area now consists of two objects, x1, x2, and two arrows, f1 and maybe I shouldn't call them f1. Let me call them h1 and h2. So the reason why we are calling these x1 and x2 is that it is possible that x1 is equal to x2, but we still want to think of them as being drawn separately. So this underlying graph I was talking about has this shape where there they are separate objects, separate entities. And so my diagram here is taking a picture like this and labeling basically objects and arrows by objects and arrows of the category. So if I call this, let's see, A1, A2, right? Then I can think of my x1 as d of 1. I can think of x2 as d of 2. I can think of h1 as d of a1. I can think of h2 as d of a2. Okay. With the remark that it's possible that d of 1 turns out to be equal to d of 2. Like in a sequence, when you take a limit of a sequence, you can have repetitive terms in a sequence, right? That's why we want maybe a sequence and not necessarily a set. Okay, so what is going to be the limit of this? So applying this general notion to the special case, what are we going to get? So the limit of this thing should be a set L together with two arrows, these projection arrows, pi1, pi2. And remember the requirement, this requirement, that the arrows that are in my yellow area, which I never had before, right? I mean, in the notion of a product, for example, of two objects, or limit of this discrete diagram, I never had any arrows inside the yellow area. Neither I had any arrows inside the yellow area here. I mean, there might have been some arrows, but I just ignored them. We're not ignoring those arrows anymore. So if I have some arrows in the yellow area, in my diagram, that is, so this thing is called a diagram. Over the graph that's drawn here. So once I have some arrows in there, I want to now impose this restriction, which tells me basically that these triangles should commute. So let's identify such triangles here. So I have, how many triangles will I have here? Would anyone like to help me here? So maybe I'll remind you what we did there. So for every single arrow in my graph, I consider the triangle. So let's say if this was arrow F3, I consider the triangle that's based on the label of F3, so in the category, so the morphism D of F3, D of F3, and the corresponding projection maps that went to projection morphisms, rather, that went mapped to the D of 3 and D of 4 respectively. And I wanted this triangle, the corresponding triangle, to commute for every single choice of arrow here. So I have two such arrows, right, in my graph, A1 and A2. So I would have two triangles, this one and that one. and I want them to commute. So a limit is not just any set with just arbitrary functions pi1 and pi2. I want these functions to interact with the functions h1 and h2 in the following way, that h1 composed with pi1 equals pi2, and also h2 composed with pi1 equals pi2 as well. Of course, in this specific case, we see that now pi2 becomes uniquely determined by pi1, right? Because pi2 is just that composite. And moreover, not just that, we also need this pi1 to be such that composed with h1 and h2, they give the same result, because they have to give the same pi2 in both cases. So another way of thinking about this condition is just a condition that kind of drops pi2 completely and just says that I've got a pi1 such that pi1 composed with h1 equals pi1 composed with h2. Now, the limit is such a diagram, the diagram consisting of L, pi1, and pi2, with the property that if I have another such thing, so if I have C with F and G, maybe F1 and F2, satisfying similar requirements, that H1 composed with F1 equals H2 composed with F1 and equals F2, then there must exist a unique arrow from C to L. Let's call this thing F bar. So there must exist unique F bar from C to L, such that the other triangles commute, these ones, namely these ones, this one and that one. So pi2 composed with F bar equals F2, and pi1 composed with F bar equals F1. So we can now say that the limit of my diagram D, so this is where I introduced the D notation there for the yellow area. So the limit of D is a system L pi1 pi2 such that H1 composed with pi1 equals pi2 and equals H2 composed with pi1. And for any system C F1 F2, with similar equations being satisfied, there exists unique morphism F bar from C to L, such that these composites are equal. So it's quite a mouthful, the definition. But now let's try to make it a bit more understandable by computing what such a limit should be. So what do you think? What should we make L to be? So when I didn't have these arrows, right? When I just had two objects like this, the limit turned out to be the Cartesian product. But now, what do I do when I have those arrows? In fact, those arrows kind of tell me that pi2 is irrelevant. It's all about pi1. And what I want from pi1 what I want from pi1 is that h1 composed with pi1 equals h2 composed with pi1. Now, coming back to the original idea of the infimum, in a way we can think of the infimum of a set as kind of most optimal object that's less than all of the things in my set, right? And this intuition for the infimum being the most optimal such will nicely guide us in finding limits of specific diagrams in other categories as well. So if you think about once again this L being most optimal, under which property? Under this property. So basically now it's really about not the L, actually it's about pi1. So what would be the most optimal function pi1 such that this holds? If you think about it, what possible functions you can create going into x1 that satisfy this equality, and then that will give us a candidate for the limit. So to approach the question from this angle, let's actually draw a set theoretic diagram representing two functions between two sets, and then we'll maybe identify what would be the most optimal way of encoding the information that I want these two functions basically after being composed with pi1 to be equal to each other. So I have two sets, x1 and x2. And let's pick a very specific pair of functions. I'm going to represent them with green and blue arrows. So the green function maps these elements as suggested by the diagram. And the blue arrow maps them the following way. So if I call these elements 1, 2, 3, 4, and 5, and those ones on this side 1, 2, 3, 4, and 5 as well. So this is the case when maybe x1 maybe turns out to be the same set as x2. And then so the function h1 is defined by mapping everything basically to itself, right? It's the identity function, in fact. h1 of x equals x all the time. And what about h2? h2 of numbers from 1 to 3 equals 1. So h2 of x equals 1 when x is 1, 2, or 3. And it equals 4 when x is 3, 4, or 5. Okay, now I want a third set L with a function going to x1, pi1, such that h1 composed with pi1 will equal h2 composed with pi2, and such that it will have the property that if I have another set, let's say C, with some function f1, having the same property, having the property that h1 composed with f1 equals h2 composed with f2, then I will want a unique f bar here going from C to L such that basically this triangle commutes. So going there and then applying pi1 is the same as f1. So we're looking for such a function pi1 here that solves this condition, that satisfies this condition rather. Now, in the example of these two specific functions at h1 and h2, what would be the most natural function you can think of, the most optimal in a sense, that will satisfy this requirement? Sorry, I made a mistake. It should have been here pi1 on both sides, and also f1, right? So now we're with a very concrete question. The first concrete question is to find a specific function from L to x1, just any function that has this property. Maybe in the beginning we should just name a few of them, just like we did here with the greatest common divisor. We just listed all possible divisors, and then we saw which one was the greatest. So maybe that would be the approach, to list all possible functions pi1 that satisfy this, and then see which one of them will be such that any other will have a unique way of connecting C with L. Or maybe we could take an intelligent guess right from the start and say, if this is supposed to be a fundamental concept, the limit of such a diagram, then surely there should be some intuitive way as to why this pi1 is natural. And so maybe the first simplest example we come up with will be the one that will solve the problem. So what would be your suggestion for defining pi1? Okay, so you see, Gregor, you said any constant function will satisfy the requirement. That's a very good point. Any constant function will satisfy the requirement, but then we'll have many different ones, and there will be no way for us to choose which one is the best. And we were talking here about one special one, right?
So if we want basically, well, so we observe that H1 and H2 agree if and only if x is equal to 1 or to 4.
Just a moment, Jean. I think you know the answer to this question, don't you? From before this lecture.
I have not seen limits explicitly before this, no.
Okay, great. Then please go ahead.
Okay, so my approach here is to say, well, H1 and H2 agree if and only if x is equal to 1 or equal to 4. If pi1 maps to anything that's not 1 or 4, then we will not get that equality.
Right.
And so therefore we want pi1 to map to exactly 1 and 4. And so the simplest case is just L contains 1 and 4, and pi1 is then the identity map.
Right. Nice. Thank you very Jean. Thank you very much. That's a very correct and very nice approach. So if we write this equality out in terms of elements, it says that H1 of pi1 of some random element in L, let's call that random element just L, must equal to H2 of the same pi1 of L. And so this object here, pi1 of L, must be an element of x1 on which H1 and H2 agree. And there are only two such. I think you said there are only two such, right? So it's 4. That also kind of links back to the idea of constant function that Gregor pointed out. So if we just had a constant function taking everything to 4, that would satisfy the requirement, and the other one is 1. So my function pi1 cannot have in its range, cannot have anything other than 1 and 4, because as soon as it has some other element in the range, as soon as there is an L for which pi1 of L is neither 1 or 4, we will never get this, because for all the other elements, for 2, for 3, for 5, H1 and H2 do send them to different places. So what we do is we take L to be basically, as you see from here, we just take L to be those x's from x1 on which H1 and H2 do agree. And we can actually now jump directly to the general case and prove that this approach will work. So And pi1 map will of course be just inclusion function, including the set L into the set x1. So if I have now two abstract sets x1 and x2, okay, so let me first complete the inequality before. So in this case, that would turn out to be the set of 1 and 4, and then pi1 will be defined by mapping x to, or rather L to itself. And so we can apply this idea in the general case where we take arbitrary two functions h1 and h2. We propose to put here in the place of L, we propose to put the set of all those x's from the set x1 such that h1 of x equals h2 of x. We have a natural function that way that maps every x to itself. Because x is such that h1 and h2 are equal, then we get this composite map, which is basically restriction of h1 and h2 on the elements on which they're equal. So this composite map maps x to h1 of x, which happens to be the same as h2 of x, according to how we chose the domain of that function. So this is our pi1 map, and this is our pi2 map. And we do have the requirement then that this composite equals that, basically by definition. And now if I have another set C and two functions f1 and f2 satisfying similar requirements, that h1 composed with f1 equals f2 equals h2 composed with f2, let's see that we can prove that there will be a unique function net going that way that will make the triangle commutative. So we're looking for a unique f bar having the property that f bar composed with pi1 equals f1. But what is our pi1? Pi1 maps everything to itself, right? So existence of this unique f bar is equivalent. I mean, of course, it will be unique because why will it be unique? Because I can actually write down what this equality says. So we're looking for a unique f bar such that pi1 of f bar of C equals f1 of C. But remember that pi1 of x is x. So we're looking for a unique f bar such that f bar of C equals f1 of C. And of course, such f bar will be unique because it must take all the C's into exactly wherever f1 takes them, right? So there's no question of no problem with uniqueness. It will definitely be unique when it exists, but the question is, does it exist? So if I begin with an element C here, right? Will I be able to map that element to? I have to map it. According to this, I have to map it to f1 of C. So will I be able to map that to f1 of C? What's the problem? Why can't I just say, why can't I just do that mapping? Well, the problem is that this set is not quite the same as the set x1. This set is smaller than the set x1. So f1 of C, which is in x1, might not fall into this set. So how do I determine whether it falls into this set or not? Well, it will fall in that set if h1 and h2 agree on that element, as Jan said, right? So is it then true that h1 of f1 of C equals h2 of f2 of C? Is that true? That must be true for every C, so that I can actually build this map f bar. Anyone would like to help me figure this out, whether this is true or not?
Yes, so I think that must be true because that's the requirement we put on C and F1 and F2.
Exactly. Yeah, that's the requirement we put on the triple C F1 F2. So we proved that we found the limit basically of this diagram. It's given by what is called the equalizer of the two functions. So this thing is called the equalizer of H1 and H2. And we now see that this is very different to the limit of this discrete diagram of two objects where it was Cartesian product. So now Cartesian product and something like this kind of become the same thing. I mean, not the same thing, but they become instances of one general concept of a limit. And there are also many other instances of that concept. A very important equalizer is when you, I mean, I'm not talking about why Cartesian products is important. We all know that. But equalizers are also important. And one example where they're important is when H1 and H2 are the same function. So if now I had a diagram with H1 and H2 being the same function, so I will just call them H, then the limit of such a diagram, so I'm just going to literally use this notation, not to have to introduce a d there, will be the set of those x's in x1 such that okay, sorry, I confused myself here. That's not the example I wanted to discuss. The example I wanted to discuss was a different one. Going back to vector spaces, if I have vector spaces V and W, I could consider two maps. So that's not the example where they're the same one. Of course, when H1 and H2 are the same one, if you look here, if H1 and H2 are the same set, so the same function, then of course these values will always be equal. So then I will get, my equalizer will be all possible x's in x1. So basically this will be the same set as this one. So that's maybe the less interesting example where the limit turns out to be one of the objects in the diagram. Just like sometimes with sequences, limits of sequences, when you've got situations where, for example, there are no new terms in the sequence, when after some point the sequence remains constant, then the limit will be that constant number, right? A phenomenon like this is happening here. But now the example I wanted to show you of an equalizer, an important example of an equalizer is where, let's say we take two vector spaces and we have some linear function h, and then we take as the other function to be the function that maps every vector to the zero vector. So h is an arbitrary linear map. And 0 maps v to the zero vector there. What will the equalizer be then? So standard notation for the special case of a limit of when it's an equalizer is this. It will consist of all the vectors in V such that h of v equals 0 of v. But 0 of v, of course, is just the zero vector, right? So it will consist of all those v's such that h of v equals 0, and that's of course the kernel of h. And this could be happening in the category of sets, but we could also think of this happening in the category of vector spaces. So we are now able to define the kernel of a linear map just using the language of the category of vector spaces. And of course, we know that in linear algebra, kernels of linear maps are very important things. And so it's nice that the limit, the notion of a limit allows us to talk about kernels, also possibly in general categories, if you want to generalize some piece of linear algebra from a specific category of vector spaces to more general scenarios. kernels are important not just for vector spaces, for many other algebraic structures as well, and in most cases they're always defined this way by equalizer of a structure preserving map and the constant map mapping everything to the trivial element. Okay, so we now looked at two different examples of a limit, a product, and an equalizer. But there are many more. So let us now, maybe it's time we formulate precise definitions for these things, and I hope that these examples has given you an intuitive language in which to understand the precise definition, which might appear a bit complex. So to define formally limits, we need to first define, so let's write this down. So to define limits, we first need to define graphs. So these are the these things, something like that, or something like that, or in this case, our graph was just consisting of two vertices 1 and 2 with no arrows between them. So we need to define what a graph is. Then we need to define what a diagram is. A diagram will take a graph. Let's say, in this case, it will take a graph and it will label. It's almost like a vector field. It will label every vertex of the graph with some object of your category, and every arrow of the graph with some morphism of the category, so that domain and coldomains are preserved. Then the third thing we need to define, a term that we haven't introduced yet, a cone. So a cone will be basically this blue data. When you got one object here and you've got a bunch of arrows going into your objects of the your values of your diagram at your vertices of your graph. So for each vertex of the graph, there will be one blue arrow going from that fixed object to the corresponding object in the category, in such a way that certain triangles commute, namely these ones. So this triangle commutes, that triangle commutes, and for every arrow in the graph, we have one commuting triangle. And then finally, state this condition saying that something is unique. That means defining a universal cone. Okay, so let's define each of these concepts, but in some cases we're going to take shortcuts. We're going to use kind of subtractive approach in some of these definitions. So a graph is a category without composition and identity morphisms. So what I'm trying to say here is basically take the notion of a category, the way we define it, and from this definition, remove everything we said about composition and remove everything we said about identity morphisms. Then you get the notion of a graph. A diagram, D, from G to C, where G is a graph, and C is a category, again, we're going to use subtractive approach here. If G was a category, then we're interested in functors from the category G to the category C. But G is now not a category, it's only a graph. And if you recall in the definition of a functor, we had this object mapping, we had the morphism mapping, and then we wanted the composition to be preserved and the identity morphisms to be preserved, as well as the domain and codomains of morphisms to be preserved. But composition does not exist in G, identity morphisms don't exist in G, so remove those parts in the definition of a functor and you get the notion of a diagram. So a diagram where from G to C, where G is a graph and C is a category, is a functor without preservation of composition and identity morphisms. Okay. Now, the next notion we need is the notion of a cone. So given a diagram D from G to C, a cone over D is a pair Cn. Maybe I'll call this not n, but let me call it L, n. Cn, where C is an object in C. So let me just write by saying that C is an element of C. And n is a natural transformation. And I'm going to put it in quotation marks here. From the constant functor from G to C, mapping all, okay, maybe defined by, I'm going to say defined by, so this constant functor, let's call this constant functor K, is defined by setting K of every X in G to be my fixed object C, and K of every morphism F in G to be the identity morphism of that fixed object. So it's a natural transformation from this constant functor to the functor to the diagram D. Okay, now here it gets a bit complex. So let's maybe make a drawing to illustrate why we're saying what we're saying here. Imagine if I have my graph consisting of two objects and one arrow between them. Let's say F. So this is my graph G. And imagine then my diagram looks like this: D of 1, D of F, D of 2. And now I have another diagram. So I should actually not call this a functor. It's rather a diagram because the domain is a graph. which maps everything here to the same object C. So C equals here K of 1. The same C equals K of 2, and the identity of C equals K of F, right? And now imagine that this was a picture from a category, and we have these two functors K and D. What would a natural transformation be? A natural transformation is a family of maps, one for each object in the domain category, right? So a natural transformation is to have this N1 component and the N2 component, and then every such square needs to commute a square that arises from specifying an arrow in the domain category. Okay, what does it mean in our context? In our context, the square becomes a triangle because these two objects here are the same object. So this is the naturality square. Becomes a triangle. The triangle goes like this: C, N1, N2, and there we have D1, D2, and D of F. And so commutation of this triangle becomes the property that D of F composed with N1 equals N2. And that's exactly what we wrote there. If we go back here, remember we had this idea that for every F in my graph, I need to have this D of F composed with pi n equals pi m. So these are the triangles we were talking about there. And of course, this is exactly the same as that, except that now we are not calling them pi n pi m. We're calling them instead n1 and n2. The notion of a natural transformation does not say anything about composition or identity morphisms in the domain category. So we could literally restate the notion of a natural transformation from functors to diagrams. So it doesn't really require changing the notion, because in a diagram, the codomain is still a category, and to state that this square commutes, that is coming from the definition of a natural transformation, we just need the codomain to be the category. We don't need the domain to be a category. So that's why we don't need to adapt the notion of a natural transformation too much. And so a cone will then be a natural transformation from a constant functor, a constant diagram to my given diagram. So then it will really look like a cone, because of these two objects being the same, then the square becomes a triangle. So that's how it starts to look like a cone. And then the universal cone. So a cone Cn over a diagram D from G to C is universal when for any, remember what the idea that the limit was something that has these arrows going into my yellow area, but then if I have something else with a similar situation, there must exist a unique arrow going that way. So for any cone, maybe I'm going to denote this with L, so that it matches with our notation for limit. So it's L with small l there. A cone L over a diagram D is universal when for any cone Cn there exists unique morphism from C to L. Let's call this morphism F. Maybe not F, maybe let's call it U. Such that, and then if you remember the situation there, if this is C and this is L, I want the unique thing here to make each of these, that one and that triangle commute. There exists more unique morphism U such that L of X composed with U equals nx for every vertex X in the graph G. So let's illustrate this in a picture. So we have this graph G, right? This is a picture for graph G. Maybe graph G just looks like this. Then I've got my diagram D that interprets this graph in the category. And then I have a universal cone, which means I've got my L. So if this is X and Y, here we'll have dx and dy. And if this is F, this will be d of F. And then, so the cone consists of an object L and this natural transformation from the constant diagram to the other diagram. So it will consist of the morphisms Lx and Ly, right? So that if I have another cone, so being a cone means that this triangle will commute for every F in the graph. And if I have another one, given by C and Nx and Ny and the whole family of n's indexed by the objects of G, then there exists a unique U such that each of these triangles, so the ones I'm going to put in the orange area here, each of these triangles commute. In other words, that its composites are always equal. Okay, so the notion is complex, as you see. It's much more complex than the notion of a limit of a sequence. But after one carefully unpacks each of these steps to arriving to the notion, then kind of the complexity kind of goes away. It becomes something natural. But then there is another complexity which comes with taking a specific category, a specific diagram in it, and then trying to compute its limit. And we have seen that in two examples here. When our diagram, the first case in the category of sets, the diagram was consisting just of, so the graph was this discrete graph of two vertices, and the diagram was any diagram over that graph. So it amounted to taking an ordered pair of sets. And then we saw that limits can be computed as Cartesian product of sets. And we had another example where our diagram was such a picture, and then the limit amounted just to taking the subset of x1 on which h1 and h2 agrees. And of course, now the question is, what about general diagrams inside the category of sets? Well, is there a way of computing the limit of an arbitrary diagram? And the answer is yes, and you might want to explore how that's done. But then knowing what the limit of a diagram is in the category of sets might not be might not help you to find out limits in other categories, but sometimes it will. And this is where this topic links up with the topic of adjunctions. So I'm not going to be able to prove this theorem now, but because we don't have enough time, but we will at least be able to formulate the theorem. So consider an adjunction. Let me try to stick to my notation for adjunctions from the previous lecture. I think we had C, D. So we wrote an adjunction out as a system consisting of C, D, and then there were the functors F and G, and the unit of adjunction and the co-unit. So on the picture, looks like this. I've got C there, I've got D here, I've got G here, I've got F here. And let's add to this picture a diagram, and let this diagram be inside the category D. But now we'll have a little bit of a clash of notation between this G there and the one we use for a graph. So I'm going to rename this to R and L, for R for right adjoint and L for left adjoint. So R and L. L is the one that usually goes on the left, and R is the one that goes on the right. So if I have a graph G and I have a diagram over that graph, so let's call my diagram D as before, then I can compose D and R to get a diagram in C. Right? Now imagine, furthermore, I have also a cone over D, which is universal cone. So I forgot to say this, but the definition of universal cone is the definition of the limit we were looking for. So remember, a cone will be given by a constant functor. So let's call this K as before, and a natural transformation from K to, so if I go back here to the definition of a cone, in item 3, a cone is given by a constant, basically an object which amounts to constant functor, constant diagram rather, and this n was the n here was natural transformation from that constant diagram to the diagram D. So I can draw it this way. So here's my n. And then I have the following theorem. So consider an adjunction and a universal cone, or in other words, limit of a universal cone over a diagram in D, as shown above. So here is my so this data of the object K and the natural transformation N is the universal cone. The theorem says that this composite diagram. So basically, you got a diagram in D, and then you apply to everything in your diagram, you apply the functor R. You will then get a diagram going from G to C, which we can denote by R composed with D. You actually even have a constant functor as well by composing K with R, right? So we could also compose here K with R composed with K. And we can even generate this natural transformation, which we will call Rn. Just by applying the functor R to the entire picture. So, I mean, imagine, for example, you had a product in the category D. So this is the category D, and this is the category C. So we have, let's say, two objects, X and Y, and the limit of those two objects, which comes with this projection maps, right? I could apply the functor. If I have a functor from D to C called R, I could apply the functor R to each of these entities here, right? I will get R of X here, R of Y, then here we'll have R of the limit. Now it shouldn't be called L because L was used for left adjoint. So let's call it lim, R of lim of xy. And I could apply R to my pi1 and pi2 to get R of pi1 here and R of pi1 pi2 here. So basically I get this cone here, the cone Rn. The theorem says that when n is a universal cone, also Rn is a universal cone. In other words, right adjoints preserve limits. So they're continuous. If preservation of limits is called continuity, then right adjoints in an adjunction are continuous. Okay, so we kind of rushed this up a little bit, for which I do apologize. But I don't want us to conclude without zooming out a little bit. So what are we talking about here? I mean, you saw how complex the notion of a limit is, right? And moreover, you also saw that computing the limit of a certain diagram might take a while, especially, I mean, maybe in the category of sets it's not so difficult, but maybe other more complex categories it would be even more difficult. However, once you've computed your limit in this category, then you can transition that computation to the other category. If you have a functor going from there to there, a functor R, which has a left adjoint, in other words, a functor that forms part of an adjunction. So it allows you to use information. I mean, it might have been, let's say, easy to compute the limit here, but maybe difficult there. But then you just apply the functor to that computation here, and you get the computation of the limit there, which will be just evaluating your functor on your diagram. Another situation is kind of opposite situation where we don't know how to compute the limit here, but if we know that the limit does exist, then we could compute it here because it's easy to do it there, and then know at least that the limit that must exist here will map here by the functor R, will map to the limit that I know how to compute there. And an example of that is again our situation of vector spaces. So let's consider these two categories, vector space and the category of sets, where we already constructed an adjunction that was mapping a vector space V to itself seen as a set. Okay. So let's try to demonstrate an application of this theorem by asking ourselves, if I go back to this notion of limit of a family of two objects, which in the category of sets turn out to be Cartesian product, and now I want to know what will be the limit of these two objects in the category of vector spaces. So I've got two vector spaces, v1 and v2, and I'm wondering what is the limit of the diagram v1, v2. If I know it exists, let's call this maps p1 and p2. If I know the limit exists, then by the previous theorem, if I apply the functor, this functor, which is a right adjoint, so if I forget that these are vector spaces, if I just consider them as sets, then this must be the limit in the category of sets. But in the category of sets, we know that this is Cartesian product. So this is how we come to the idea that maybe this must be a vector space whose underlying set is the Cartesian product of those two vector spaces, and not maybe, but actually for sure, because of the theorem. And after this, the computation of the limit becomes much easier. Now we're looking for a vector space structure on v1 cross v2, which would make pi1 and pi2 maps continuous. And of course, that uniquely determines the vector space structure. Because of continuity of pi1 and pi2, you will basically end up with the Cartesian product of vector spaces. So the fact that right adjoint preserves limits can be made use of to describe what limits will be in the category of, at least to get the first step in describing what limits will be in the category of vector spaces, based on knowing what the limits are in the category of sets. Okay, so just to conclude with a very brief conclusion, the purpose of limits in general is to describe mathematical structures that are constructed in a complex way from other structures. In many cases, it turns out that there is a certain diagram you need to produce that whose limit will be your structure. So the notion of a limit kind of brings together various constructions in abstract mathematics, and then the insight that the limits are preserved by junction. That insight is useful in understanding the behavior of this construction based on behavior of similar construction in a different category.